There are two prominent techniques which is used for secondary structure determination. One is circular dichroism, another is Fourier transform spectroscopy. And since proteins are in watery sample, it is difficult, so lots of methodology is developing. Not only for NMR, formation of hydrogen bond happening or not, tangent hydrogen bond, formation of all of us know disulfide bond form होता है, कैसे पता करोगे disulfide हुआ है या नहीं? प्रोटीन में सबको पता है ना डाइसल्फाइड बॉन्ड फॉर्म होता है. कैन यू फाइंड इट आउट वेदर डाइसल्फाइड बॉन्ड इज फॉर्म्ड और नॉट? एक्सपेरिमेंटली वैलिडेट इट. कैसे करोगे? ऑल ऑफ यू आर बायोलॉजिस्ट.
Sir, upon adding of beta marker pressure, the mobility should change.
मोबिलिटी शुड चेंज.
Disulfide bond टूटेगा तो it will move.
ठीक है, अच्छी बात है. तो मोबिलिटी इलेक्ट्रोफोरेसिस करोगे और उस पर चेंज हो गया, मान लो चेंज नहीं होता तो IR में बाद में आते हैं, वहीं तो मैं जाना चाहता हूँ. और कैसे कर सकते हो? मान लो तुम्हारा बेटा मर्केप्टोइथेनॉल डाले 5% टूटा और बाकी नहीं टूटा, हाउ डू यू नो? या 20% डाइसल्फाइड बॉन्ड ब्रेक हुआ गया, एसएच हो गया, बाकी एसएस रहा, हाउ डू यू नो? 2 बैंड दिखेगा क्या उसमें? तब तुम्हारा प्रोटीन इम्प्योर हो जाएगा. एनी अदर वे?
एज और एसएस का वाइब्रेशनल फ्रीक्वेंसी तो अलग हुआ.
नहीं, वहाँ मैं आता हूँ, लेकिन पहले वहाँ आने से पहले मैं और टेक्निक जानना चाहता हूँ जो तुम आज से पहले इसके बारे में सोचते थे. हाँ, इलेक्ट्रोफोरेसिस इज राइट आंसर, बट सपोज इट्स डज नॉट हैपन फुल्ली, इट्स हैपन पार्शियली. एनी अदर टेक्निक जो आज क्लास में मिस किए हैं उनके लिए घातक हो सकता है, क्योंकि ऐसे ही क्वेश्चन आ सकते हैं अभी. राइट? Anyway, so you are right. One option, if you think logically, SS bond ka electronic cloud is very different than SH bond. If you can detect this difference, you know that SS is there or SH is there. You can even quantify it, how much SS is there, how much SH is there. Have to do a careful experiment, optimization with a standard and all. But this is the way. Another way that I was, you probably not know. It is a NMR spectroscopy, because SS bond and SS bond will again have a different electronic cloud, therefore chemical shift of the NMR peaks is going to be different, and that is the another technique which can help you in finding it out whether the disulfide bond has formed or it is like this. Right? So, the two spectroscopic technique can confirm you and quantify you for formation of this. Electrophoresis is good, but you need to have 100%, either this or that. 5-10% you cannot find it out, right? Okay. Coming back to now what we discussed, the FTIR, it is excellent tool for secondary structure determination. We are mostly looking at the NH frequency, bending, stretching, and CO for getting out our structural formation. So, if you look at your helix, your sheet, right, sheet helix axis is like this, your hydrogen bond is like this, sheet axis is like this, your hydrogen bond is like that, anti-parallel is like this, parallel is tilted. So, in all three cases you have a different set of hydrogen bond in different electronic cloud, and therefore that shift happens in the frequency, and that is used for deterministic chemical shift for alpha helix, beta sheet and random coil. Right. So, there are various mode, bending, stretching, which gives to FTIR, and the CO that we are talking, carbonyl, we can call it amide 1 and amide 2 spectra, that is a CO frequency, and amide 1 is of great value particularly because that gives the secondary structure information. So, for alpha helix it is around 1650, for beta sheet we give 2 peaks 1632 and 1685, and random coil it is 1658. For a protein with all conformation, all 4 will appear. So, as I was saying in the previous discussion, that None of the protein will have exclusive, mostly like 90% protein will neither have exclusive alpha, exclusive beta. There is some percentage of helix, beta sheet and all those. But what we get typically one frequency which is something like this. But we know that, so if I just put it 1600 centimeter inverse and 1700 centimeter inverse, we have everything here, right. It is a contributed by helix sheet random coil. Now your job is going to be deconvolute it and find it out. You have become the expert from the UV visible. Same question you have to do it, but I will give you some example as we go. So what are the other application of FTIR other than the secondary structure determination? Identification of exchangeable group in the any biomolecule. Say let us take it protein. When H is replaced by D to D, IR spectrum will change. Where H can be replaced by D? Ionizable group in protein. Where are ionizable group in protein?
Acids और OH basically.
OH वो तो निकल जाता है, कोई भी प्रोटीन में ना टर्मिनल OH वैसे ही भागा रहता है. There is, it does not stay because it's a in the deuterionic form of a protein COO minus and NH3 plus is there. Any other group?
Side chain.
Side chain. Which side chain?
CONH2.
CONH2. Is that acidic? No. Side chain CONH2 you are talking about of asparagine and glutamine. Does that NH exchange with water? No. Very high pH. Protein उसमें जिंदा कहाँ रहता है भाई? Right. We let's talk it in reasonable pH, say pH 5 to pH 8. That will remain there. Which exchanges, which proton or which is aspartate and glutamate? After pH 4 they are also not there. Right. Aspartate and glutamate COO minus, right? It is just as a COO minus. H is gone already. That after 9. Arginine, lysine, histidine, excellent. pH 6.5, histidine side chain wants to roam around, right? That is a neutral pH. And most importantly, all the backbone NH is labile. Backbone NH, if it is not hydrogen bonded, they are labile. ये पता है या नहीं? Am I saying something different? Backbone CONH. Remember this structure of a backbone CONH, right? I am talking about this guy. Is it labile or not labile? Here is my partial negative charge, here is my partial positive charge, and this is a dipole, right? Each amide is a dipole. This is labile. Right? If you put it in a certainly higher pH, not even 9-10, your each proton has a tendency to roam with water, exchange with water, right? It exchanges with water, and since it is in water, so NH you cannot see. But suppose I put this NH which is labile in a D2O, what will happen? They are exchanging with a D. Now instead of NH it is a ND, and ND will have a different frequency than NH. We can find it out whether this proton is exchangeable or not exchangeable, whether it is buried inside or exposed. So this gives the idea of a proton which is buried, which is exposed. Another one sometime back they said about histidine NH, that also if you are at above 6.5 it exchange and you can replace that with a D. So those are the ND, you can find it out which proton is exchanging, which is buried, and you can find it out. So identification of number of hydrogen bond that is there. सारे प्रोटीन में सारे हाइड्रोजन बॉन्ड नहीं हो सकते ना. There are like 100 amino acid का प्रोटीन, there are 50 hydrogen bond only. Rest are hanging around here and there, right? So हाइड्रोजन बॉन्ड होंगे जहाँ हेलिक्स होगा, जहाँ बेटा सीट पैरेलल एंटी पैरेलल होगा वहाँ पर. So and सबकी हाइड्रोजन बॉन्ड की स्ट्रेंथ भी अलग अलग होती है, right? If it is on the surface, although it has formed the hydrogen bond, but probability of its exchanging is fast than the other proton which is buried inside, जहाँ water penetrate कम कर सकता है. So you can find it out, the hydrogen bond measurement of their breakage during denaturation. So all those can be done with FTIR. For a chemical reaction, keto-enol tautomerism, it's in ketonic group or OH group. You can find it out because ketone has a different frequency than alcohol, right. Interaction with a small molecule, I showed you free HSA, free DNA and when complex form. Similarly, you have a protein and ibuprofen, HSA with ibuprofen, and ibuprofen binds, some change should happen. You can monitor that change that is happening. If it is observable, it will show in the IR spectrum, right. Similarly, the hydrogen bond will form between bases and they will shift, right. So, titration of protein carboxylic group, you can titrate with a different pH and find it out. Now, so what happens that, okay, let me just skip because I did not discuss with. So, basically what we are talking about, that IR has a distinct pattern of absorption, and already we have discussed this Franck-Condon principle, right. So, like a Franck-Condon principle, what was it saying, you remember?
By the time electrons are making the transition, nucleus is stationary.
Right. So, nucleus is, so therefore, the contribution that should come from nucleus does not interfere here as well. So, why electronic transitions between vibrational state of different energy level, that is straight line. So, here vibrational also follows the same rule that was for the UV visible. Now, let us go back to again the same concept of 3n minus 5, 3n minus 6. So, degree of vibrational mode for a linear molecule that we have seen are 3n minus 5 and non-linear 3n minus 6, right. So, suppose we have a 3 atoms. So, 3 into 3 minus 5, vibrational mode for CO will be 4, for water 3 into 3 minus 6, that will be 3. So, this is the water vibrational frequency, symmetric stretching and all those. So, water molecule display 3 fundamental vibrational, symmetric stretching, asymmetric stretching and bending. What CO2 will have 4 one of them is not IR because this is just like this. So, based on these, for different moiety there is a different frequency, and this is the list. Unfortunately, there is no thumb rule that you have to, I can tell you, you have to have these numbers in your mind, that if something is coming from CH3, it will show around 1400, if it is CO, it will show around 1600 to 1700. Similarly, NH, NH2, all those will have a different. Now, coming back to SH, I was talking about SH. See SH 2580, OH 3600. So, hydrogen bond में H है या OD हो गया, that you can find it out by looking at here. So, these are some of the fingerprints that are there in FTIR. Similarly, for the protein, you can use this similar concept to deconvolute it and find it out. So, for these proteins, if the secondary structures, where are the secondary structure information coming in the protein, from which frequency? Amide 1, right, which is CO. CO means ketonic group wala, 1600 to 1700. So, we in FTIR we do the experiment. I will just take the next slide and come back here. So, this is the frequency we are talking about, amide 1 frequency, CONH, right, amide 1 vibration. So, if it is helix or sheet, it shifts little bit. Now, you record the protein spectra, but I am not zooming, it is going from 400 to 4000, but I zoom only this region, which is 1600 to 1700 centimeter inverse. This is the frequency where my secondary structure is buried inside, right. So, this is the frequency amide 1 and there is amide 2, but let us fix on this. Now, here as I was saying, it is contributed by a helix, coil, sheet. Sheet may be parallel, anti-parallel, right, and you know that it is a little bit shift, right, if you remember 2-3 slides back. For random coil, beta sheet, helix, that was there. Now, suppose I am giving you the spectra which is like this, I had drawn earlier. So, suppose I did my FTIR experiment by somehow getting rid of water. Here is my 1600 centimeter inverse, here is my 1700 meter inverse. This is what we are getting from FTIR. But I know from like our understanding, a sheet, a helix and a random coil are here. These are the three things. Now, if experimentally we are getting this experiment and theoretically we know that these are the typical frequency, can you find it out the percentage? What is the percent of helix, sheet, random coil in a typical protein? You understand what I am saying? So, this is say 100% sheet, 100% coil, 100% helix, right. Here is whatever you remember 1600, 1670, 6058 or something, those frequency we know. Now, what we get is overlap of all this frequency. You have to deconvolute it and find it out how much is contributed by this, how much contributed by this, how much contributed by this. So, this is the curve fitting exercise that one has to do to find it out exact percentage of helix, sheet, coil. So, essentially what we are doing? We are taking this experiment, doing this and probing this CONH, getting a spectra like this which is amide one, and now we fit it and find it out. This is the percentage that this protein will have. So, just look at these numbers. FTIR calculated for a hemoglobin 78%, beta sheet 12%, TORN 10%, and random coil they could not find it out by FTIR. Then they crystallize the protein and find it out 87% helix, 0% beach sheet, 7% TORN and some random coil 6%, right. For other protein, so that is why using CD, 68 to 75, 1 to 4, 15 to 20, 9 to 16. So, look at these three top. What is your observation and what is your conclusion if you have to draw something? Yeah, what you can draw from here? Look at myoglobin 85, 85, 86, right. Lysozyme 40, 45, 29 to 45. Cytochrome 42, 48, this. Here sheet is also something like this. So, what I want to emphasize that these are the simpler technique FTIR and CD, and X-ray requires longer time. First of all, you have to be very good with your hand, that you crystallize the sample, get a single crystal, you are diffract it and then solve the structure. उसमें बहुत time लगता है, right? आजकल robots आ गए हैं, they can screen all the conditions and in one condition you get the crystal, but it's a art. It's an art to get a good crystal. Crystallographer का life इसी में चला जाता है कि कब good crystal मिला, then they are very happy, right? So it takes time to get a good crystal in crystallography, but here you don't need any crystal, you don't need to wait for that long time and pray that one day your crystal is coming and it is diffracting. Just start a solution and do FTIR, you are getting more or less similar percentage of structure, not details, but if your job is only to find it out percentage of the structure, secondary structure, you can get it. But where to where, that can come from crystallography or NMR. To start with, these are the good fantastic technique to find it out percentage of helix, sheet, random coil. And look at all of these that we have, three techniques we have compared, most of them are in good correlation. The three techniques is giving you same structure. So, for all sorts of complex protein you can find it out. Now, how you do experiment? All the protein will be in some buffer. So, first you have to record the buffer, subtract the buffer contribution and you can get the spectrum something like this. So, remember your real spectrum of a protein is coming like this. What was this guy? Huge wala, right, OH, water, coming from water. Where we are interested? CO, right, this one, right, this one. So, here we are interested. So, right, so if you just take a protein contribution, some contribution comes and then you have to base correct it and just focus on this guy, and now here you have to zoom it for deconvolution. So, that is what say we are zooming it and then we are fitting it of this bigger protein that I was talking to you. It is a big helix protein, you remember helix protein. You can fit this guy and then you find that 95% of this is helix and some 4-5% is a coil. Now go back, we have a structure of this, it is a mostly helical protein. So that is good part of your FTIR, that helps you in getting this. So what you have to remember, your alpha helix frequency, your beta sheet frequency, parallel anti-parallel, beta 10 frequency and some non-recognized one. The another thing, if you are getting too complicated, you can put that in D2O. What is good part of D2O? It will attach to the exchangeable proton and it will shift the frequency. So in D2O, some of those helix shifts by few centimeter inverse, and you can have shifting in the sheet, random coil, wherever it can incorporate, and you can see the shift. So sometimes, many times you do in D2O as well, right. So just to get rid of water, you put it in D2O, some frequency shifts happens, but you can do in the D2O. Essentially you have to do this kind of curve fitting, secondary structure determination by means of ATR FTIR spectroscopy, where you get this curve like this, you fit this different secondary structures, helix, sheet, random coil, parallel, anti-parallel, none of all those, and you can find it out how much, which kind of secondary structure present in a particular protein, right. I told you that D2O will have some different frequency. Why is so?
O and B and O and H.
Very good. Bond exchange. The same thing can be just seen by isotope effect that we are talking about. So you see, I talked to you, these are springs. So you have a harmonic oscillator kind of behavior, and harmonic oscillator, when these two are there, then there you can consider the reduced mass. So O16 versus O18 or H1 versus H2, the reduced mass will change, and therefore you can even predict it, how much change in the frequency should happen. So if you just take it O16 versus O16, O18 versus O18, I left it deuteron because of its a smaller change, but O18 is significant. You can have the change in the frequency, and that is what is the isotope effect. So if you are doing your experiment in deuterium, there will be some shift, which I was talking to you 2 slides back, because H is replaced by D, D molecular weight increases. If you consider that harmonic oscillator, the frequency will shift. Therefore, in deuterium you will absorb some shift in the frequency of the protein. That is a simpler concept. Okay, I just want to give you one good part. The FTIR is so good, so why just stay up to 1? One can do 1D, you can do even 2D IR. It is not so popular as NMR. NMR is very cleaner one, but still it is a evolving field where you can do the 2D IR, similar like NMR pulse sequence. You can have a IR pulse sequence. You have to have a pulse like a laser which excites in a IR frequency. This is the 2D IR. You have one time domain data, second time domain data, and detect it. You get a correlation peak and a cross peak. Correlation peak means same wala, cross peak, those are talking to each other. So actually in you can, this field is also expanding towards the 2D. A method is developing. There are some groups all over the world which are pushing IR in the higher dimension, because it has a profound application in many of the interesting biomolecular observation, and therefore water is not good. So we want to get rid of water, and you can do in D2O or go ahead and do something else. Now this enters into the another kind of a spectroscopy. Water is not good for biology, water is unavoidable. So can't we think something else?